We're going to talk about slope and in particular derivatives. If you want to get a little refresher on slope of a line or even functions, we have some introductory videos for that on the mathmusicandmore.org, so you can go there and look at those if you want to brush up on that first. But we're going to dive into basically slope and derivative here. What we'll do is we'll start with a story. I chose this as an example to try to show how you can get this math stuff to relate to reality. It's pretty cool. So let's imagine that you're standing at a start line, kind of like a drag strip, let's say, a raceway, and the person's going to drive away from you and they're going to put the pedal in the metal. So they're going to have just no change in the pedal. They're just going to stomp on it and go the whole way. And also suppose you had a little laser rangefinder of some kind that you could aim at them and you could quickly write down the distance away from you every second, let's just say. I'm theorizing that the curve of when you got done graphing this curve, which again we talked about before, but when you get done graphing it, if you had time going like this on the x-axis and you had the distance away on the vertical axis, you might have something like this, this kind of a shape. I've chosen this function because it's a good way to talk about the shape of the curve and the derivative and the results and that kind of thing. So what we have here is a parabola. It's an exponential with a power of 2. And in this case, as time goes by, if I were to try to show, as time goes by, the distance away is climbing. And what's interesting is when you start from 0, of course, the amount of distance changing is not as much. And then later on it's covering more distance, and so in effect it actually does get flatter in a way. But the acceleration really isn't changing, but we'll get to that later. So this is the graph of distance over time. So it's interesting that I use the word over because it turns out that at any moment you do have a speed. And this is where we start getting into slope. So I'm going to show just one moment in time here as an example. Let's just pick 6 seconds just for fun here. And if you can imagine the speed you're traveling as equating to the slope at that moment, that's kind of one of the keys to this whole thing. So if we imagine we're right at the 6-second point, we could have sort of a surfboard here that rides along this curve. And at this point, if you were to place it on the curve, and it would have to be tangent, that's the word we use, but it just touches only at this exact spot. It actually isn't touching anywhere else, even though with the thickness of the lines it actually looks like it's overlapping. Mathematically, it's only touching at exactly this spot right here at 6. Excel is saying 8, but it's this point right here, 6. So it's 6, and then 180 is the, I'm sorry, 108 is the vertical. At that spot, if we were to lay this tangent line to give us the slope and then extend it out far enough to draw a triangle, remember that line, equation of a line we talked about before, it does go on forever. But of course we can pick any 2 points we want. So I kind of randomly picked 4 seconds as a distance across here. And then the difference in the height will be the distance change across this particular slope triangle. So it turns out that the slope, as you probably recall, is rise over run, so it's going to be the change in y here, this distance, divided by this distance, which happens to be 4 seconds. Now where things get interesting as far as curves and math and applying it is the fact that slope actually has some meaning here. The slope, in fact, is the speed at that moment. If you look at the units, you'll see that's pretty clear. You take meters and divide by seconds and you get meters per second, and the slope then is in fact your speed. So that's kind of interesting. So the slope's changing, which means your speed's changing. The slope is increasing because it's getting steeper as you go. So that is a representation. The slope is actually a representation of your speed at any moment. So why is that interesting? Well, it's interesting because in calculus with the derivative, you can take this function right here, this expression of this function, and you can take a derivative of it, and you can calculate what the new curve will be that represents the slope of this curve. So let's take a look at that. Now you may or may not have already heard the formula for taking the derivative of a function like this. If you haven't, what you do is you take the exponent here, the 2, multiply it by the 3 and get 6, and then you reduce the exponent by 1, which brings it down to a 1. So you wind up with y prime, which is one way of we write the derivative. This derivative function then becomes 6x. So what's really cool is that this graph, this function, this curve, the height of this curve at any moment is in fact the slope of that curve. So if you recall, we said at 6 seconds, we said the slope was 36. That means if I go over here and look at 6, then the height of this function should be 36. Not the slope, but the height. And you can see that at 6 seconds, in fact, that's about what it is right there. So that's very powerful now because you only measured distance. That's the only information you wrote down. But with math, you can tell somebody that at 7 seconds they were going a certain speed. And that's cool. So if I hit go here and you watch, what's happening is the slope, see the slope, see how it's slowly increasing? With every second that goes by, that slope is going up. And I'll try to stop it right at 6, but it's close. So the height of this function is actually the slope of that function. That's a physical way of looking at what a derivative does for you and how it can be useful. So here we have 5.7 seconds. We have a slope of 34.2. Here I chose 2 seconds as the time window to figure out what the size of this triangle is. So I've got 2 seconds this direction, and then whatever the height difference is for that particular slope. So that's what these numbers mean. You can pick any 2 points. Remember that. I just arbitrarily picked 2 seconds as a span to show the little surfboard, if you will. So it's really important to understand that when you take the derivative of a function, the resulting function is actually a graph of the slope of that original function at any moment in time. So the value here is equal to slope there. And if you notice something right off the bat here, this is a straight line. That means that the speed is increasing evenly. If you remember, we made the assumption that the person stomped their foot to the floor and never varied the pedal. The fact that this line is straight is representation of that. If they had eased off on the pedal partway through, this curve would have turned downward a little bit. So that's kind of cool. So that goes to show the usefulness of math like this for something really practical, where you can start analyzing the movement in different ways without ever having even recorded that data. That's very cool. So what's really even cooler is you can take this a step further and you can start with this curve. And you can say to yourself, well, what would happen if I do that again? What would happen if I took the derivative of 6x? What do I get? What does that mean? Well, remember that here we took a graph that had meters over here and seconds over here, and when we got done, we got meters per second. So we always take this divided by that because that's the slope of this. So what do you get over here? Well, it turns out that when you take a speed curve like this one, and you take the derivative with respect to time here, which is what we're doing, you wind up with meters per second per second. That is a rate of change of speed rather than a rate of change of distance. A rate of change of speed is acceleration. And so what you wind up with if you take the derivative of this is the acceleration curve. And if you recall, I said the evenness of this line is representative of the person having the foot to the floor the whole time. The flatness of this curve is the same thing. If the person pulled their foot off the pedal, the acceleration would, this is almost like a representation of the pedal position, if you will. That would mean this would come down if they had decelerated. Now again, this is all theoretical, not accounting for any other variables. This is just sort of in theory. So anyway, so the slope then of this curve is represented by the height of this curve, just like before. And as we said before, since this slope isn't changing, it makes total sense for this to stay constant. And the rules of derivatives still apply here, so there's a 1 that's not shown here. So to get from here to here, we just took the 1 multiplied by 6, reduced the 1 to 0, which x to the 0 is 1, it leaves you 6. So the math all works out, but even more interesting is that the math works in terms of like physics and understanding what's happening. So what I thought might be a fun thing to do here is to actually look at something actually happening. Let's imagine we have a little car here. And if we were to watch this car, you would notice that it actually is not moving very quickly at the beginning. That's representative of these distances all being small down here. And as time goes on, it's covering more ground in any given second, and the speed's increasing. I didn't bother graphing a bar here because that's pretty boring. What's interesting here about the speedometer is that the even increase is represented by an even rotation speed. So it's interesting that the accelerator pedal is well named because the pedal does in fact represent directly acceleration, not speed. And if you were curious to see this in miles per hour, we can do that, and you can see that in miles per hour, this isn't quite a quarter mile, but you can see the actual speed in miles per hour, and it actually is pretty quick by the time they get to 300 meters away. I'm making Excel work pretty hard here. I may have a delay in it that's a little too long, making it slow. The only other thing that's really interesting to notice is that with your eye, as you watch the car move, when you're in this range, the whole right half here, your eye doesn't really notice mathematically these slope changes on here. You don't really notice those. You notice it at the very beginning because it's very flat starting from 0. But you don't really notice it later because you can see it's kind of flattening up here. So anyways, so I hope that you found that interesting and helpful and informative, that you can see that math is actually useful for something practical. It's not just numbers and theory. So I hope you enjoyed that, and I'll be working on the next one to talk about some interesting things about sine and cosine. Thanks.